Hello, in this video we're going to go over a bit more complex app, following up on the basic template app for console. This one is actually going to do some acoustic signal processing. I already started it. I'm using the OASIS-dev deck box this time rather than the board by itself. Here you can see a sonar transducer as well. Let's get our help menu. Here there's a number of functions available, but I'm going to concentrate for the purpose of this video on signal and noise monitoring, M. And here it's running now. Notice this LED here now started blinking, and that's of some significance later on. I'll get back to that, but keep that in mind, the blinking LED here as we start this test. What is the output of the test? We get evaluation of peak signal strength and average signal strength. Here it's always the first number is at the output of the analog front end of the receiver / the input of the ADC, and then the second number here for the peak and here for the averages is at the output of an FIR bandpass filter centered at 33.9 kilohertz. Let's just concentrate on this second average number. So after the filter, what's the signal amplitude? Average minus 70 dB, respective full scale. So 0 dB would be the largest number. And if I just scratch the sonar transducer, you can see this number here going up by, what, 20 decibels, give or take. So just by lightly scratching against here. So it's quite sensitive. So before we look at the code, let's review how the EM60 receiver actually is structured so that you can make sense of it. And here we go. Here's a diagram of it. This stuff is inside the MCU, and then this one here is on the board level. So we have the sonar transducer here, signal amplifier, then an anti-aliasing low-pass filter. The output of that goes into the A to D converter here. Then there's a DMA controller that streams stuff automatically to this ping pong buffer. It's interrupt driven. We'll have a look at that. Putting the first 256 samples into buffer number 0, then the second 256 into number 1, and then going back to 0, 1, 0, 1, and so on. Once a block transfer is done, there's a processor interrupt, and the DSP, the MCU now initializes the DSP coprocessor, so the LEA, in our case, to perform an FIR bandpass filter. The results are stored in an output buffer, and then the CPU evaluates the output buffer, producing some signal statistics that you saw, and these results are then going through the USB interface. Looking at the application structure next, let me maximize this. We will use the standard hardware drivers and standard power switch and LED, no changes here relative to the basic template app. Acoustic data streaming, we use the DMA operated ping pong buffer. Then we do an FIR filter at this level. And here at the acoustic data analysis, we do some simple statistics, the results of which you have seen. All right, with this knowledge now in place, we can now look at the actual code structure. I'm starting with main.cpp, and it's essentially unchanged from the template app, except for the new application name is inserted here. Moving a level up, base.cpp, also the same, except for the baud rate is set to 115,200. Instead of 9600. The reason for that one is that right now serial data transmission is not on the interrupt level. Serial data reception is. And so when you print a string at a slow baud rate, it could take so long that you get a buffer overflow on the acoustic data processing buffer, you know, the input side, the DMA ping pong buffer. So we went to a faster speed. That's really just a band-aid. The real solution is to also make the serial data transmission interrupt driven. So you're really just writing to a buffer, and then from there it's transmitted a character at a time based on an interrupt basis, or based on DMA is even better. So that'll be in the next version of the API. Gives you an idea as to sort of how the API will advance. Moving up from the base, the next level up is where EM60 self-tests is defined. So that's the class that implements the various self-test functions. And I'll first look at the header so you get an idea as to what's going on. So here's this class. There's a bunch of protected functions, and we will concentrate just on monitor mode here. And then the only public one is where self-tests itself actually gets called. So let's move on to the code here, specifically the monitor mode function. What we see here is first the low frequency receiver is initialized, and we provide pointers to the location of the shared LEA RAM. That's a limited amount of RAM that's available in this MSP 430 device that can be accessed by both the CPU and the LEA, the DSP coprocessor, and it's very fast RAM, but a limited amount. So we are, putting stuff here, and another video will show you how to do your memory allocation. Here's the buffer size. I'm sorry with these mouse overs here. Buffer size, how many samples, sample frequency, 125 kilohertz. And this 2 is actually the duty cycle. So we're not processing all data. We are getting 256 samples, then skipping 256 samples, then going to the second buffer, getting 256 samples, skipping 256 again, going back to the first buffer, and so on. So that's initialized here. It's not actually started. The receive streaming is not started at that point. That happens 2 lines down. Here we are initializing the FIR filter, and this 0 means channel number 0. It's set up to support 4 FIR channels, 4 frequency channels. This is to implement some frequency hopping acoustic communication protocols. Here we are just using channel 0, the first channel, where the data is going to be in SBUF DMA. So it points to the whole buffer here, and the FIR will notice it's really a ping pong buffer. Then where are the coefficients for the FIR filter? How many of them are there? Sorry, where are the coefficients to be stored? How many of them are there? And where can you find the coefficients? And that's in this file. And I'll get to this file and coefficient generation for FIR filters here in a moment. Next step here, LFRX set. This is where the receiver is actually activated, and then on an interrupt basis, this will all happen automatically. Then once our initializations are done, we go to a main loop, and we just keep checking if data, serial data is there. It'll keep running until somebody hits a key, any key in this case. So as long as nobody's hit a key, it moves on here. It checks if there's a buffer overflow, which means that some data has been lost, and there would be an error message if that happens. So that's for your debugging purposes. You're trying to do more than can be done. And then it checks if buffer 0 is full, and down here if buffer 1 is full. So it checks them both. If one of them is full, it performs some statistics here. What's the peak signal? What's the average signal? Signal bias? That's the stuff that you saw printed out. Once that's done, we go down here, sorry for the mouse over, into FIR execute. We're now performing an FIR process, in this case on buffer 0. Down here it's on buffer 1, so you see the ping pong stuff. And we are storing the results in sbuf results. And then we do the DSS, DSPS stats, the signal statistics again. Yeah, so doing them again, this time from using sbuf results. So the output of the FIR filter was up here. It was directly in the DMA buffer. So what does it look like after the FIR? That's the minus 70 dB that I pointed out, that is then here finally processed. Here's our average and our bias. And then so this is all averaged over multiple buffers. And then once we reach a certain buffer count, then we do our printout of statistics here. Okay, going back to how the FIR works and how you define an FIR filter, because of course you can have any number of possible FIR bandpass filters, low pass, high pass, whatever you want. Notice here in this FIR initialization call, we have FHPP, FIR, HFB, high frequency band channel 0. And those come from here. And here they are. This is the .c file, and there's an associated .h file. So where does that come from? Well, how do you know? How can you define this? Oh, this one says it's sampled at 125 kilohertz, and these are the cutoff frequencies, lower and upper one, But where do all these coefficients come from? It's actually super simple. Texas Instruments provides a nice tool. It has a curiously generic name of just DSP-lib GUI, so you wouldn't really know that this is about making FIR filters, but that's what it is. And you just select a few things. Here it just says example FIR, but you can change the name. That will become the file name. Generally, you use Q15, which are 16-bit A to D values that are used here, are represented at 16 bits, even though the A to D is just a 12-bit. And here we have FIR or IIR selection. Here we can do band pass. What else can we do? Band stop, low pass, and high pass. So there's a few options here. The type of filter is a Bartlett filter. The filter coefficients are important. If you put 62 in here, you actually get 64 coefficients. And in the next video where I talk about memory allocation, that is of some significance here. As you'll see, the sample frequency pass bands start and end, and then you get this output here. I can change something, like hopefully it won't crash. I'm going to make myself twice as many, or let's say 126 coefficients, and let's see if this becomes a sharper filter or not. Yep, now you can see the filter is much sharper here, right? But also there's a lot more coefficients, so it's a lot more computing power. Also, here's the impulse response, which, by the way, got slower by having such a sharp filter. The old, relationship that a filter that's narrow in the frequency domain will be wide in the time domain, and vice versa. And then all you have to do is hit File, and if you do Export Filter, there's a menu that pops up. It's kind of slow on this one for some reason. Eventually, it'll pop up, and you just enter the folder, really. And the name of it is defined here, and that gets you the coefficients that you saw in our source code. All right, to conclude this video, I want to show you something here. Notice this LED flashing. I pointed that out in the beginning. It starts flashing when we're in monitor mode. So arguably when we exit monitor mode, it should stop flashing. Let me exit monitor mode. Oops, wrong scope here. There we go. But it keeps blinking. How could that be happening even though monitor mode is stopped if this is related to monitor mode? So let's look at a part of our application code here in specifically ISI interrupt service routines. And you don't really have to modify them, but here you can see that part of this DMA interrupt service routine, the LED is switched off if it's on, or switched, well actually here it's switched on if it's off, and here it's switched off if it's on. So it happens in this interrupt service routine that this LED blinking is generated. And what happens in the interrupt service routine, without going into too much detail, is that it's called whenever the DMA controller has finished filling a buffer, so completed 256 samples, then this is called, and various stuff happens where the DMA is reinitialized. We see that here, and where the ping pong action takes place. So the fact that the LED is still blinking, even though that monitor mode stopped now, means that this still happens on the interrupt level, and it demonstrates actually that, you know, stuff happens in the background on the interrupt level, even if your main code is no longer running something. So what's the cause of this? If I go to the self-tests monitor mode here, we can see as we entered monitor mode, we initialized the DMA here and started it here. I'm sorry, LFRX set mode detect. Then when we exited, we should have switched it to mode off, and we didn't do that. So even though we are now in the main menu, we can see that here again. We're in the main menu. I can hit the help or whatever, and the LED still keeps blinking. Well, I could exit self-tests here. It will automatically re-enter it, but sort of initialize it, and now you can see that the blinking stopped. So I hope that gave you an idea as to a structure for a bit more complex application that does acoustic signal processing. There's a lot more into it, and you can kind of check that out yourself. Like on the transmit side, here's ping sequence test. You can run that. You can inspect the code. GPS test to see how the GPS is operated, or full acoustic modem function. So go explore this self-test application, and it'll give you a good idea as to how to program acoustic apps for OASIS, the OASIS architecture and boards in general. Thank you very much.